Welcome to iLectures Online, and this time I'm going to show you an example where we have a proton that has a mass of 1.67 times 10 to the minus 27 kilograms entering a chamber parallel to the floor with a velocity of 5 times 10 to the 5th meters per second. A magnetic field of 0.4 teslas is directed from the floor to the ceiling. What will be the radius of its motion if it has a charge of 2.5 microcoulombs? And no, a proton would not have that kind of charge. The charge in a single proton would be 1.6 times 10 to the minus 19 coulombs. All right, that's much better. Okay, so what do we do here? Well, you have to remember, when a charged particle moves through a magnetic field, it's going to feel a force perpendicular to its motion, which causes the particle to deflect. And as it deflects, the force continues to be perpendicular to its motion, which causes the particle to go around in a circle. And so the objective of this problem here is to find the radius of that circle, the radius of the motion of that particle, in this case a proton. So let's draw a picture of what's going on here, and imagine that we're looking at the chamber from above, so a bird's eye view of the chamber. And since the magnetic field is directed from the floor to the ceiling, it would be coming towards us, so we can represent the magnetic field in that chamber by the tips of the arrows like this. This indicates that the magnetic field is coming from the bottom up, like so. And so we have the B field. The magnitude of the B field equal to 0.4 teslas. So now we have a proton, which is a positive particle, moving through the chamber with a velocity v. And the question now is, what will be the direction of the force? So you use your right hand rule, you point your fingers in the direction of the velocity, and then you move your hands in such a way that you can curl your fingers in the direction of the magnetic field, and your thumb will point in the direction of the force. So in this case, the force will be downward, like so. Now the force is going to deflect the particle. The particle is going to start moving like this. And of course, since the force continues to act perpendicular to the motion of the particle, it will continue to deflect it in a circular path. And so the question is, what is the radius of that circular motion? Like so. The way you do that then is to realize, back from mechanics, that whenever something goes around in circles, it does so because there's some centripetal force. F centripetal, which of course, according to Newton's second law, is equal to m times a, mass times acceleration. Of course, in this case, it's a centripetal acceleration, and the definition of the centripetal acceleration is mv squared over r. And then you say, well, what is causing that centripetal acceleration? What is causing that force, causing it to move around in a circle? That, of course, is the force due to the magnetic field. And the force due to the magnetic field is equal to qv times b times the sine of the angle between the direction of the velocity and the direction of the magnetic field, which, since it's always perpendicular, the sine of 90 degrees is 1. So we can simply write qvb. And then if we compare these two or write them equal to each other, the centripetal force is equal to the force due to the magnetic field. Sometimes we write F sub b to indicate that's the force of the magnetic field. We set the two equations equal to each other. We can say that mv squared over r is equal to q times v times b. Then we realize that there's a v on both sides of the equation, so that cancels out. And then solving this equation for r, you can see then that we can move the r up here and the qb down here. So we can write that m times v divided by q times b is equal to the radius of that circular motion. Then all we have to do is plug in the numbers for those values, and we get the radius. So let's try that. So radius is equal to the mass times the velocity over the charge times the strength of the magnetic field. So the mass given to us at 1.67 times 10 to the minus 27 kilograms. The velocity, 5 times 10 to the 5th meters per second, divided by the charge. The charge of a single proton is 1.6 times 10 to the minus 19 coulombs. And then finally, the magnetic field is 0.4 teslas. All right, so where's our calculator? Let's figure out what that is. So we have 1.67 e to the 27 minus. Very small mass times 5 e to the 5th equals, divided by the charge, 1.6 e to the 19 minus, and then finally divided by 0.4 equals, and the radius r is equal to 0.013 meters. So the radius is equal to 13, let's see here, that's not 13 centimeters, that's 13 millimeters. That'd be a pretty small radius, so about this big. So as soon as the proton enters the magnetic field, it'll start going around in very little circles, and that's the motion of a charged particle in a magnetic field. Now, units-wise, how did I come up with meters? Well, let's look at the units. We had kilograms. We had meters per second. We had coulombs. And then we had Teslas. Now, a Tesla, by definition, is a Newton per ampere times meters. And of course, the units of an ampere is coulombs per second. So we can replace that by coulombs per second, which is seconds over coulombs. So seconds over coulombs. Getting rid of the amperes like that. Now notice that the coulombs cancel out. We have meters over seconds, and we have seconds here. That would be seconds squared. We have meters here and meters at the top. That would also not cancel out. So let's simplify it a little bit. We have kilograms in the numerator. We have meters in the numerator over seconds, so seconds comes down over here. That would be seconds. We have newtons in the denominator. Now, a newton is a kilogram meters per second square, so we write kilograms meters per second squared, but since it's a denominator, then second squared goes into the numerator, second squared. We have 1 over meters here, that brings meters to the top. And we have seconds in the denominator, so that gives me seconds in the denominator. All right, so what do we have? Kilograms cancel out, meters cancels out with this meter, seconds and seconds cancel out seconds squared here, and we're left with meters, which is, of course, the answer that we got over there. So units seem to work out as well. And that is how you figure out the radius of curvature of a charged particle moving through a magnetic field.